So let's say question number 35 was from fluid mechanics in session 1. You will get a question very similar from fluid mechanics in the evening session at 35. But they will just change values and maybe give some different kind of concept. But more or less, it stays the same.
When did they go for more session, like session 1, session 2, session 3, for more competition, or in comparison to like more candidates applied for GATE examination due to that reason?
I
What?
think, yeah, I think there are a lot of candidates, and everyone cannot give this computer-based test at the same time, right? So that's
Yes,
why
sir.
they do session 1, session 2. But this has been going on for I don't know, maybe for a very long time, because you will always see set 1, set 2, set 3 from mechanical. So those are always there.
Like I last time I followed 2016 was it went for 3 sessions.
Maybe there were more number of students in 16. Usually it's set 1 and set 2, I think.
Huh.
Yeah.
Even 2009, perhaps 19 was also 3 sets.
Mm,
19 or 9. Actually, I'm messing things up.
could be 9. I think 19 was only 2 sets. Yeah.
Because there are total 27 years, 27 previous year questions from 2009 to 2022. So therefore, I
Yeah,
was
yeah.
calculating
Yeah, and ideally you should solve all the 20, what is that, 27, 27, 28, whatever
27,
years.
27,
Yeah,
27 up to 2022.
yeah, yeah. You should solve all those 27 years question. Then you can really expect a good score, I feel. But yeah,
So
anyway.
during this preparation, one thing I have realized that practicing previous year question means like covering all the topics and gaining question from those topics.
Yeah, yeah, yeah.
That's it. Yeah. So there's
In GATE, that's what you need to do actually. Like by heart all the previous year questions, and more or less the new exam will be on the similar concepts. Okay, anyway,
yes.
let's start today's discussion. So today we'll be doing heat transfer, as some of you had asked for it. So I'll only cover topics which are in black, and I hope you have covered conduction and convection heat transfer by yourself or in by maybe some in some other live session. But today we will be covering radiation part of the heat transfer subject. And so I was looking at the previous years, and see most of these questions are coming from either Wien's displacement law or view factors. So we will be doing questions from these two topics mostly, and let's see how many we can solve today. So let me just start. Okay, so this is from last year's exam, and this is very easy question. Again, this is from Wien's law. And the question says that Wien's law is stated as follows. So they have already given you the Wien's law, which says that lambda corresponding to the maximum emissive power. So that is the lambda subscript m times the temperature is a constant, which is given by this 2898 value. And lambda m is the wavelength at which, so yeah, they say that emissive power of the black body is maximum for a given temperature T. Now the spectral hemispherical emissivity of surface is shown in the figure below. The temperature at which the total hemispherical emissivity will be highest is. So this is a 2 marks question. I don't know why they gave it as a 2 marks question. Basically, you just have to get T from where at 6,000, because they are asking you because lambda m will be 6,000, as that's the location where the emissivity is maximum from this curve. And then I guess the Stephen Boltzmann law, all of you guys already know. So then this is very trivial. So just write it down. So emissivity is the ratio of emissive power of a black body, emissive power of a body to that of a black body, and that's from the Stephen Boltzmann law. You can say that emissive power is given by epsilon sigma t to the power 4, where epsilon is the emissivity. Now they have given you that this curve is a variation of this emissivity with respect to the wavelength, and lambda t is constant. This lambda t constant is is the so here lambda is the that wavelength where the power is maximum. So let's say if I plot emissive power, which will be E with respect to lambda, so you get a curve like this, and wherever this curve is maximum corresponds to your lambda m. So once you have lambda m, finding out temperature is simply C divided by lambda m. And in this example or in this question, they've given that emissivity maximizes at 6,000. So for our case, lambda can be taken as 6,000 in angstrom units. And then this is just 2898. So this is in micrometer, so you can just do 10 to the power minus 6. And this is 6,000, but this is in 10 to the power minus 10. And then the temperature you will get, it will be in kelvins. I guess you can. So one of you can, I guess, solve it and then just let me know what the answer is.
Four eight three zero.
Yeah, it should be, yeah, 4830. Thank you. So the final answer will be 4830 Kelvin. That's all. Okay, so let's now move on to the second question. This is again from last year's paper. So here they say that a flat plate made of cast iron is exposed to solar flux of 600 watts per meter square at an ambient temperature of 25 degrees Celsius. Assuming that the entire solar flux is absorbed by the plate, cast iron has a low temperature absorptivity of 0.21. Now use Stephen Boltzmann constant of 5.669 into 10 to the power minus 8. Neglect all the other modes of heat transfer except radiation. Now, under the aforementioned condition, the radiation equilibrium temperature of the plate is. So, now for this question, you need to know something called as the Kirchhoff law. So, this Kirchhoff law just says that the absorptivity and the emissivity are same for a body when the radiation coming from the black body is close to the temperature of your original body. So we will see this through this question itself. Let's just draw the configuration. So maybe this is our plate. So this is our plate. and let's say it has some temperature Tp, and this is the temperature we need to find. Now there is some solar flux or some solar energy coming, which is 600 watts per meter square. Let's denote this with S here. So some S is coming onto this plate. Also, you have some ambient temperature here. So it's like some sky or some atmosphere. You can think of it like this. Let's call this as T infinity, the temperature at which the sky is. And this is given as 25 degrees Celsius, or you can say just 298 Kelvin. Now, since this has some temperature, this will also radiate. And let's say the radiation coming from this is given by so this will be given by sigma T infinity raised to the power 4, because the sky is like a black body which is emitting towards the flat plate. Also, since the plate has some temperature, you'll see that the plate will also radiate back, and since this has the temperature Tp, it will radiate like sigma Tp raised to the power 4. So this is radiating away from the plate, but since the sky is radiating towards the plate, some of it will be absorbed, and that will be given by this absorptivity. So the rate of change or the rate of heat transfer from the plate will be equal to, let's say, the incoming. So I think this, like this. Yeah, incoming energy minus the outgoing energy. The incoming energy comes from the sun, plus it comes from the radiation of the sky, and since there is an absorptivity of 0.21, so only 0.21 of it will be absorbed. So alpha here represents the absorptivity, and this we can just say sigma T infinity raised to the power 4. This is the incoming energy, and the outgoing energy is the radiation from the plate. So this is the emissivity of the plate times sigma Tp raised to the power 4. Now they have given us that we need to find the equilibrium temperature. So at equilibrium, we can say that at equilibrium sigma t, the rate of change of the rate of heat transfer will be equal to 0. And once we have that, then the incoming and the outgoing has to balance. So then we have sigma Tp raised to the power 4 is equal to the solar flux plus the amount of energy from the sky being absorbed by the plate. Now here, since the plate, since the sky has this temperature, which is the ambient temperature, and the plate temperature will be close to it, we can use our Kirchhoff law and say that alpha will be equal to epsilon. Then it becomes just a matter of calculating t to the power 4. So that will be s plus alpha sigma t infinity raised to the power 4 divided by epsilon sigma, or we can just say alpha sigma, better. I will put down the values. Please tell me the right answer to this. Final answer I want. So this is 600. Alpha is 0.21. Sigma is, you can just call it 5.67 to 10 to the power minus 8. And T infinity is 298 kelvins. And this is again 0.21 into 5.67 into 10 to the power minus 8. So this is your TP. Now just tell me the final answer here. Did anyone solve it?
Yes, sir.
What is the final answer? Anyone?
Is it 491.3?
Mm,
Same answer.
Or it is in Kelvin?
218.33.
yeah, yeah, yeah. So yeah, that's what I was looking for actually. 280. So
सर
please,
वो
yeah,
केल्विन
yeah,
से करना भूल गया.
yeah, exactly. So see, the question is simple. There is nothing in here. And the problem is they will try to trick you with the units in the end. So you have to be careful. Just subtract whatever you get and subtract 273 from it because in the end they want answer in degree Celsius. And this formula is applicable when you have the temperature in Kelvin. So it's just like the absolute temperature. So whenever you are solving it, please convert it into Kelvins and just check at the end what units they are asking the answer in. I think most of the chances of mistake is in the unit conversion here only. And please make sure to always check your calculation and the units.
Sir, here solar flux and solar radiations are different.
Solar flux is solar flux, right? So only what do you mean by solar radiation? Solar flux comes from the solar radiation. So there will be some sun here, let's say. It will have some temperature, right? And it will radiate on its own temperature. Let's say the temperature of the sun is Ts. So it will radiate like sigma Ts to the power 4, and then that will be felt as S here. So that they have done this job for you and they have converted it into S directly.
Then in expression of Q dot, we are doing S plus that
Yeah,
something.
yeah. This is the energy from your atmosphere. So atmosphere will have different temperature. No? Sun is different, and then there is this atmosphere, let's say, which has clouds and everything. It has a different temperature, and this also does some radiation. So any body which has any temperature which is greater than the absolute zero temperature will have some radiation, and that is that radiation.
Sir, I want to ask a thing that
Yeah.
as absorptivity 0.21 is given, so वह मतलब इससे ऊपर स्टेटमेंट में ऐसा क्यों लिख दिया गया है कि 600 मीटर स्क्वायर पूरा एब्जॉर्ब हो जाएगा?
Oh, this is, oh, no. See, this S is being absorbed completely.
फिर एब्जॉर्बिविटी का रोल ही क्या हुआ? मतलब उसकी तो मतलब सर बेइज्जती कर दी ना.
No. See, it will absorb the solar radiation completely. Solar radiation comes in a different wavelength, and this radiation coming from the sky will come in a different wavelength. So it absorbs the short wave coming from from the solar from the sun completely.
ओके सर, समझ गया जी.
Yeah. So they are in different wavelengths, so the absorptivity will be different.
So absorptivity for higher temperatures is closer to 1.
You cannot say that in general. Absorptivity depends upon the material. It will depend upon this plate. So for this particular plate, the short wave was completely absorbed, whereas the long wave this uh, coming from the atmosphere was not absorbed completely. It had absorptivity of just 0.21 for this.
Okay, sir.
Yeah. Okay. Let's just move on to the next question now. So this is from 2021, and the question is: a solid sphere of radius 10 mm is placed at the centroid of a hollow cubical enclosure of side length 30 mm. The outer surface of the sphere is denoted by 1 and the inner surface of the cube is denoted by 2. The view factor F22 for radiation heat transfer is. So let's just see what view factor is. So simply view factor accounts for the effect of orientation on the radiation heat transfer between two surfaces. So let's say I have some surface here, and I can think of it as point source, and you have three kind of plates. So you will see that the radiation which is emitted by this point source will directly affect this, because this is horizontal. It has like the maximum surface area. Here it will have zero effect on this plate because it's just exactly vertical, and here it will have some somewhere in between the vertical and the horizontal case. So what this shape factor does is basically accounts for the orientation between the two surfaces, and this is usually denoted by Fij, where Fij means the fraction of radiation leaving surface I. So let's say this is our surface I and this is our surface J. So Fij will be the fraction of the radiation leaving this point source I and then striking the surface J. Right, so that's what the shape factor is. And here I've taken some example from again this. So I think in last classes when we were doing fluid mechanics, I was taking some illustrations from the fluid mechanics book by Sengel, and they have another book called the heat transfer, and you can also go through it. It's a very nice book. They have very nice illustration on conduction, convection, and on radiation heat transfer. I've taken this from that book, and here you can see that there are these three different geometries, and so Fij means we just saw that the fraction of radiation leaving I and striking J. But what does FII mean? FII is basically leaving the same surface and then striking the same surface. So for a plane surface, this will be zero, which is that makes sense because it cannot come back and strike the same surface again. So for a plane flat surface, F11 or Fi to I is zero. For a convex surface also, this will be the same. So since no radiation can come back and strike the same surface again, so in this case also F22 is 0. But when you have a concave surface, you can actually see that there are these rays or the radiation which strikes the surface, the same surface, and then F33 is not equal to 0. So this is just illustration of the shape factor. Now, one interesting or very important thing you should always notice that when there is a surface enclosed onto an outer sphere or any outer surface, then the the radiation which leaves the first surface, the enclosed surface, and strikes the second surface will always be 1, because whatever leaves from the inner sphere here will always go and strike the outer sphere. So in this case, F12 becomes 1. Keep this in mind because this will be used in lot of the questions that we will do, and then I guess you might find a question like this in the next in the coming exam also. So there are these two relations also you should keep in mind. So this is called as the reciprocity relation, where the radiation leaving surface 1 and striking surface 2 times the area of surface 1 is equal to the radiation of surface 2 striking surface 1 times the surface area of 2. Also, there is this rule, the summation rule. So this is just saying that if you have, let's say, one plate and then you have four different plates. So in that case, let's call this 1, 2, 3, 4, 5. So basically F11 plus F12 plus F13 plus F14 plus F15 will be equal to 1. So it will have the summation of one everything leaving from 1 and striking all these other surfaces will eventually amount to 1. And in our case here, since F11 is 0 because it's a plane surface and it cannot strike itself again. So we get that F12 till F15, summing them up gives you 1. So this will also be used when we are solving questions. And if we know all of this, let's see how we can solve this question. So they are saying that we have a solid sphere of radius 10 mm and it is placed at the centroid of a hollow cube of length 30 mm. So you have let's say some kind of a sphere here and it is enclosed in some cube. So let's call yeah, cube is denoted by the inner surface of cube is denoted by 2. So this is 2 and this is 1. Now we are supposed to calculate F22. Now we just saw that when there is this enclosure, that means that F coming out of 1 and striking 2 will always be equal to 1. So then we can use the reciprocity relation and say that F12 times A1 is equal to F21 times A2. Now A1 and A2 are simple to calculate. So for a sphere, the surface area will be 4 pi r cube, and for your cube it will be 6 faces of 6 squares basically, so 6 times L square. So from here you can get F21 which will be equal to F12 times A1 over A2, and F12 we just saw is 1, A1 is 4 times pi times r cube, which is oh, this should be 4 pi r square, not cube, sorry, because this is surface area. Yeah, so this is 4 pi times 10 square, and you have 6 times L square, where L is 30. So this gives you F21. Now, since we are asked to calculate F22, we can use the summation rule and just say that F21 plus F22 will be equal to 1. And then F22 simply becomes 1 minus F21. So that will be 1 minus 4 pi into 10 square over 6 into 30 square.
0.7673.
Yeah, I think, yeah, this is correct. So it will be somewhere around 0.77. Yeah, so that's the final answer. So keep the setup in mind because that's what I'll ask you to do in the next few questions. And there have been a lot of questions very similar to this. You just need to see how to use the reciprocity relation and then the summation tool. So we'll come back to that, but let's do a different sort of question now. And this is from the Wien's law. And the question is the spectral distribution of radiation from a black body at T1 3000 Kelvin has a maximum at wavelength, some wavelength lambda max, they are calling. The body cools down to a temperature T2 if the wavelength corresponding to the maximum of the spectral distribution at T2 is 1.2 times that of the original lambda max. Then the temperature T2 is. So, yeah, as I was saying, that then you have to use the Wien's displacement law. And here, again, I've taken this from Single. They have drawn the distribution of emissive power, variation of emissive power with respect to wavelength and for different temperatures. So you can see that as you increase the temperature, the wavelength at which you find the maximum power keeps shifting to the left or keeps decreasing. So that's why you have lambda m being inversely proportional to your temperature, or or you can just say lambda m times t is some constant c which is given by this 2898 value. And here so this is that black dotted curve is the locus of all the maximum powers given by lambda t is equal to 2898. So for our purpose we just need to remember this lambda m times t is a constant, and then it is straightforward to solve this question. So we have been given lambda max, and corresponding to that we have been given a T1 which is 3000 Kelvin. And they are saying that if you bump up lambda max to 1.2 times lambda max, you go from T1 to T2, and that T2 is not known to us. But we just saw that lambda 1 T1 will be equal to lambda 2 T2 using the
2500
Wien's displacement law.
2500 Kelvin.
Yeah, I think, yeah, this is the right answer. So yeah, basically you just do T2 is equal to T1 times lambda 1 over lambda 2. So T1 is given as 3000. Lambda 1 is just lambda max. And this is 1.2 lambda max. So if you do that, then you will eventually get 2500, I guess. Yeah. So this is like a simple 2 marks question. And they will probably ask you again if you are lucky in coming exams. So yeah, let's see this one. This is like a quick question that we just did some theory based on this. Can anyone answer this? So sphere 1 with diameter 0.1 meter is completely enclosed by another sphere 2 of diameter 0.4, and the view factor f12 is, so this is your sphere 1.
One.
Yeah, exactly. So this is 1, this is 2, and since this is completely enclosed, everything which leaves 1 has to strike 2, and in that case f12 becomes 1, right? So let's now move on to, yeah, very similar question from the one we did for the Wien's law. I will ask you guys to solve it and just give me the final answer for this one. I hope everyone knows how to do this now, because this is just what we did in the last class only.
1000.
B.
Yeah, right. So yeah, the right answer is B. If someone is having trouble solving this, they can just let me know. Otherwise, this is what you need to apply. And this can be your T1, this can be your lambda 1, and this can be your, yeah, lambda 2, and you have to calculate T2. All right, so let's see this now. This is little a bit complicated, but okay, if you apply logic, this can also be done easily. So they have given you three sets of parallel plates, LM, NR, and PQ in figure 1, 2, 3. The view factor is, they have just defined the view factor here, and assume that the value of FLM and FNR are zero point 0.8 and zero point 0.4. So this is 0.8, this is 0.4, and they are asking you to calculate the value of FPQ. So this is not given to us, and this is what we have to find. Any idea how we can do this?
0.6 final answer.
Yeah, yeah. So how did you do it, Prinka?
For figure 2, we will get 0.4. So
Mm-hmm.
uh, if we compare it with figure 1,
Yeah,
then from L to that center slab, it will be zero point 0.4.
yeah, right,
Then it will be equally distributed to the other two sides. So
right,
if
right.
we divide by 2 and then applying it to third figure.
Yeah, yeah, exactly. So yeah, you can use you can take a help of symmetry and then do this. I think that's the right way of doing it quickly. And yeah, we can just see this for someone who has not solved it. So this is our first configuration, and this is our second configuration. And for these two configuration, we have been given the shape vector value. Now you can use one property here, that you can break a complicated shape into a summation of simpler shapes. So let's say that this is L, okay, this is L and this is M, and we just call this as plate 1, and we you can call this section of plate M as 2, this section of plate M as 3, and this section of plate M as 4. Now this is your N and R, and let's just call this as plate 5 and plate 6, and similarly for this, so this is your plate P and plate Q. Let's just call this plate P as 7, this part of plate Q as 8, and this part of plate Q as 9. Now uh, FLM is the total shape factor or view factor, which basically means the radiation which leaves 1, or which leaves the plate L and strikes the plate M. You can actually break it down into F2, F12, sorry, plus F13 plus F14. Right, and then similarly here, well, here it is just straightforward. So this can be just written as F5 to 6, and here it will be FPQ will be equal to F78 plus F79. Now you can use the information given here. So F56 is given to you, which is zero point 0.4. Now you can see this configuration F13 will be equal to F56, because they are like just the same configuration basically. And this will also be equal to F78. All these three are zero point 0.4. Also, from the arguments of symmetry, you can say that F12 will be equal to F14. So then this FLM basically becomes, so FLM is given to us is zero point 0.8. So we can say that FLM just becomes, okay, maybe I should also say that this F1 to F14 will also be equal to F79, and and yeah, so this F79 is what is actually unknown here. So yeah, let's just say that FLM is equal to F12 plus F13 plus F14, and F13 is, we just found out is zero point 0.4, so you can just say that this is F79, 2 times F79 plus zero point 0.4. So this means that F79 will be equal to zero point 0.8 minus zero point 0.4 divided by 2. So this is zero point 0.2. So now we found out that F79 is zero point 0.2. Also F78 is zero point 0.4. And finally we need to calculate FPQ, which is the radiation which leaves P and strikes the plate Q. This will be the summation of F78 plus F79. So then this becomes zero point 0.2 plus zero point 0.4, and that will be your final answer. So it will be 0.6. Yeah. So here I guess you don't need to go do all this calculation. You can actually quickly use the logic and just say that this will be zero point 0.6. But I wanted to make this explicit and then just do it step by step. So it will not basically not take you this much time if you just logically see that okay, this has some symmetry here, and this plate and this plate, the information for the two plates are given to you, then it just becomes a matter of doing pluses and minuses. That's all.
Between plates changes, then that value of view factor changes or not.
Can you repeat your question?
If
And
distance between plates changes,
yeah,
then this view factor will change. Yes or no?
no, no, no. This is
O-
yeah. I don't think this is dependent upon.
orientation change then change, no?
या सर डिस्टेंस पे डिपेंड नहीं करेगा क्या?
I don't think so. It's, let me think about it. Yeah, it's a good question actually.
As per the formula, it will depend, no, sir.
Uh, which formula?
I think so.
Which formula?
No.
No, the general formula, which is derived for shape factor,
Yeah, yeah, yeah,
cos
yeah,
theta
yeah, yeah. There is
divided.
some. Yeah, yeah, yeah. I remember there is some cos theta element there, right? Cos theta, and there is some.
Yes,
Yeah,
sir.
there is some
And
R there. Yeah, yeah, yeah. You're right. You're right. Yeah, it should depend. Yeah, thanks for bringing this up. Yeah, you guys are right. There is this R in that general shape factor formula, which is like the distance between the two surfaces, some perpendicular distance between the two surfaces, I think. So yeah, it will depend. But luckily for this case, I guess it is just 1 meter, so then it becomes inconsequential.
Okay, sir.
Yeah, yeah.
Okay, sir. Okay.
Let's move on to this one then. So this is Okay, this you can, I think, quickly tell me what the answer will be. So the emissive power of black body is P. If the absolute
16.
temperature is doubled, then the emissive power becomes
16.
yeah,
16.
yeah. So again, we're using the Planck's law. This is proportional to the T to the power 4. And then if you double it, then it becomes 4, basically 2 to the power 4, which is 16. Yeah. So this is straightforward. And then, yeah, let's see this one. Consider the radiation heat exchange inside an annulus between two very long concentric cylinders. The radius of the outer cylinder is R naught and the inner cylinder is Ri. The radiation view factor of the outer cylinder onto itself. So you have some kind of configuration like this. So two very long cylinders are there, and this is Ri. So this is Ri. Let's just call it 2Ri for now, and this will be 2Ro. And if you call this one and call this one as 2, they are asking you to calculate the radiation view factor of outer cylinder onto itself. So F22 is what we have to find. Yeah, I think you guys can try this and just tell me the final answer.
D.
Yeah, that's correct. So is there someone who could not solve this one? Yeah, just let me know. I'll solve it. Otherwise, we can move on to the next one. Mm. Yeah, let me just give you hints if someone is struggling with this. So again, F12 will be equal to 1 because this is like an enclosed thing. And then because we have to calculate F22, we can just say that F21 plus F22 is also equal to 1. But F21 times A2 is equal to F12 times A1. From here you can calculate F21, which will just be the ratios of A1 and A2 because F12 is anyway 1. And once you get that, you can plug this here and then just say that F22 is equal to 1 minus F21, or better yet, 1 minus A1 over A2. That will be F22. And then it's just a matter of calculating area for the inner and the outer cylinder. And then when you do this, you will get a T as the final answer. Yeah, we solved it in the last code. So this is there, and then yeah, let's see this question also. A very similar question. So a solid sphere of radius r1, which is 20 mm, is placed concent concentrically inside a hollow sphere of radius r2, as shown in the figure. The view factor F21 for radiation heat transfer is. So we have to calculate F21. Again, you can use the same principles. Let's call this, oh yeah, this is anyway given as 1 and this is given as 2. So then f1 going to 2 is 1, and then we can say that f21 it
B,
should
sir.
be, what did you say, Abhijit?
B 4/9.
Yeah, I think you're right. So this is equal to a1 f12, and then f2 simply becomes a1 over it. And you should know the formula for the area of the sphere, so that is 4 pi r1 square over 4 pi r2 square. Pi gets cancelled, and this is r1 over r2 to the whole square, which then becomes, yeah, r1 is, what is r1 here? Yeah, 20 over 30 square, then this is 4, so that will be the correct option, 4 over 9. Okay, so already in the last slide just said this is 4 by 9. Yeah, I think that's all I had in terms of slides here. Anyone? Yeah, okay. Yeah, thanks Priyanka for putting that on the drive link on the chat. Yeah, that is there. So this again, if someone new has joined, we will.
Yes, sir.
Yeah,
Fluid
Akash,
mechanics taught by you, sir.
can you repeat? Sorry.
Fluid mechanics.
Fluid
Is fluid
mechanics.
mechanics taught by you?
Yeah. I was taking fluid mechanics. Yes. If you want, you can check those slides.
Sir, please send the link of this also.
I think it is there in the same link which Priyanka has sent. You will find all the videos as well as the slides there. So you can just check that out.
Okay, okay.
Okay. Yeah. Anything else, guys?
So next week class is there.
Uh, yeah. I think yeah. Next week will probably be the last week. I think the class is there next week. Your exam is when?
4th February.
Okay. Yeah. So yeah, we will have one more session next week.
Then again, third part would be started for next year get aspirant.
Yeah. I don't think they will start it this soon. Maybe after a couple of months. I'm not sure.
Actually, as far as I have heard that it would be started from in the month of April or May.
Yeah, so couple of months, I guess.
Yeah.
Yeah.
Thank you, sir.
Yeah, sure. Anyway, guys, I don't think there are any questions, but please keep on solving questions and keep on practicing, and please give test series, because I've been telling everyone who has been coming to sessions that test series are the real uh, like judge of your preparations, because here you can solve these questions, but in the test series when you have exam like environment,
Yeah.
it's a bit different. I don't want you guys to lose marks just because you made silly mistakes. I'll tell you that feels worse. So if you don't know a question, it's okay. I mean, you are like, okay, maybe you were unlucky, you could not prepare the topic, or the question was extremely tough. But knowing the question, knowing how to solve it, and then committing a mistake, that hurts the most. I'm speaking from experience. So please, guys, keep practicing and keep giving these practice exams. You have still 1 week. Even if you can give 4 or 5 exams, I can assure you, you will increase 4 or 5 marks in your final exam. So I mean, don't compromise on giving exams, please.
Okay.
Yeah, if there are no other questions, then I will wish you guys all the best for your preparation and uh, happy weekend also.
Many thanks.
Yeah. Bye, guys.
Thank you, sir.
Yeah. Bye bye. Take care.